Today's topic is Z transform and its ROC properties. Let us see the definition of Z transform based on Laplace transform. We are already aware that Laplace transform is transformation of time domain to S domain, that is frequency domain. So Z transform is a special case of Laplace transform and results from applying the Laplace transform to a discrete time signal. As we already know that a time domain function xt can be represented in Laplace transform as xs given by integration of xt e to the power st for a limit of minus infinity to infinity. So as we can see that Z transform is a special case for discrete time signal. So as we can understand, in discrete time signal means if we have a time domain signal, we have to discretize it in terms of samples. So let us consider that each time interval is delta t. So let us replace the time domain information by t equal to n delta t. That is to derive the Z transform from Laplace transform. So it changes to summation n equal to minus infinity to infinity limit delta t tends to 0. That means the time interval between two samples is almost very negligible. That is, more number of samples we take, that means the more smooth will be the signal. So we replace t equal to delta nt in this Laplace transform. So t is replaced by n delta t, and e to the power st is given by minus s n delta t. So it is presented by e s delta t minus n. So the first term becomes xn. As you can see, it is a discretized form of xt, continuous time to discrete time. So xt changes to xn, and e to the power s delta t changes to z. So we can ultimately represent Z transform as xz, that is, from Laplace domain it is transferred to the Z domain equal to summation n equal to minus infinity x n, that is discrete signal, z to the power minus n. So this is the formula for Z transform xz. Now let us consider how this transformation maps the S plane into the Z plane. As you can know, when we transfer the Laplace transform in S plane, that is, S plane can be represented by the real axis and the imaginary axis. Okay, and this is the total thing of S plane. Now we can recall that in a continuous time signal represented by ct over here, continuous time signal is stable when its force lies in the left half plane, that is here. Hence, a discrete time system is stable if its poles are inside the unit circle. Now there's a question, what is unit circle? Unit circle, just like Laplace domain we have S plane, here we have Z plane. So S plane can be represented in Z plane. So in Z plane, similar to the S plane, we have real axis and imaginary axis, and this circle is the radius of unity. The radius is 1. So in other words, we can say the Z transform behaves much like Laplace transform and can be applied in difference equations to produce frequency and time domain responses. That means the left hand plane pole will be represented in the unit circle, within the unit circle in Z plane. Now let us consider, already in this slide we have derived the relationship between Laplace transform and Z transform. Now we will discuss about the Z transform and discrete time Fourier transform. As we have already seen, Z transform is for discrete time signal. So we will compare it with the discrete time Fourier transform DTFT. Now to derive the relationship between Z transform and discrete time Fourier transform, let us derive the DTFT by setting Z equal to R e to the power j omega. This is very important. Z e to the power j omega. So we already derived the equation for xz equal to summation xn z to the power of minus n, z to the power of minus n. So we are replacing z equal to R e to the power j omega. So z is replaced by R e to the power j omega. So ultimately we will get summation n equal to minus infinity to infinity xn R e to the power n. We break it as R e to the power minus n, right? And e j omega n minus g omega n. So you can see that if we this e to the power j omega means we have one circle of unit circle. So this term is nothing but DTFT of DTFT means discrete time Fourier transform, that is Fourier transform of discrete time signal. So xn r to the power of n. So the ROC is the region for which summation xn r to the power minus n less than infinity in terms of discrete time Fourier transform, which depends only on r equal to mod z, just like ROC in the S-plane for the Laplace transform depend only on real value of sigma. If the unit circle is the ROC, then the DTFT xj e j omega exists. This is the relationship between DTFT and Z transform. That is, if we replace the Z by R e to the power j omega, we get the equation as xn r to the minus n, nothing but DTFT. Let us consider an example of Z transform. Let xn equal to a to the power n un. As you can see, un means unit step response, that is 0. This is magnitude of 1. This is t. So ut in terms of let us consider n because it's a discrete time signal. So we will consider n equal to 0 for n greater than equal to 0 and un is equal to 1 0 for n less than 0. So obviously it is a right hand sequence. That's why it is written right hand sequence. So let us consider the formula for Z transform. Xz is given by summation n equal to minus infinity to infinity x n z to the power of minus n. So we replace xn by an un and z to the minus n. So already you have seen that un exists only for positive values of n. So the limit changes to n equal to minus infinity to 0 because from minus infinity to 0 un doesn't exist. So the limit changes to n equal to 0 to infinity. This is right hand sequence. So an z to the power of minus n. So let us simplify this one equal to az to the power minus 1 n factor common. So it is nothing a geometric series. So if the geometric series, so n we put 0, the first term will be 1, then az minus 1, like this it will go on. So this is nothing but a geometric series which simplifies to xz equal to 1 by 1 minus a z inverse. The ROC is given by a z inverse less than 1 or z mod z equal to a. This is the ROC. So ROC is outside the circular radius a and includes the unit circle, which means that this DTFT exists. Also note that there is a 0 at j equal to 0, as you can see over here. Okay. and this is the unit circle of radius 1, and this is of radius, sorry, A. So ROC includes the unit circle, so the system is stable and DTFT exists, okay, as well as Z transform exists. Now stability and ROC. Stability and ROC. For a greater than 0, xn equal to a to the power un, as you can consider the previous example, and this is the Z transform that we have derived, and this is the ROC. So let us consider a value of a is equal to 1.1. If value of a equal to 1.1, is the system stable? Let us see. If a is equal to 1, if the ROC is outside the unit circle, then system is unstable. If ROC is outside the unit circle, the signal is unstable. Similarly, if the ROC includes the unit circle, then system is stable. This is ROC is outside the unit circle. ROC includes the unit circle, then system is stable. This is very important. As you can see, if this is the unit circle, this pole is outside the unit circle, so it is unstable. If ROC includes the unit circle, then the system will be stable. This is the important point for the properties of ROC to get the system, to determine whether the system will be stable or unstable. Let us consider some more examples. A is equal to -1. In the previous example, we had considered A is equal to 1.1 and 0.9. So obviously we can see the ROC is outside the unit circle, the system signal will be unstable. Similarly, this one, the ROC includes the unit circle, so the system is stable. Here we consider xn to be un, that is unit circle. So A is equal to 1, so obviously we will get xz equal to 1 by 1 minus z inverse. Previously we had considered right hand sequence, this is left hand sequence. See, we had if we take un a to the power n un, so this is right hand sequence, that is like this. And for this one we get so left side, this is 1, this is minus infinity, this is 0, this is plus infinity, this 1, this value is 1, okay. un this is un minus n minus 1. So this is a left hand sequence, so the limit changes to, this will be -1, minus infinity to -1, and here we are taking negative values, so this negative sign will be repeated for every term, so let us take the negative sign common, and we have a to the power minus n, because here the limit is changing to minus infinity -1, as in terms of the left hand sequence of unit step response. So it simplifies this to 1 minus 1, because here this can be broken as the first term to be 1, then the limit will be changing to n equal to 0 to infinity, and we will change this term to a inverse z to the power n. So this is basically a geometry progression, and this term for n if you Let us clear this one. If you break this, one, then let us consider the first term, that is a minus infinity z to the power infinity. Then like this you consider, then you take n is equal to say minus 2. So in that case, a to the power minus 2 z to the power 2. Then you take first term, that is n minus 1, so plus a to the power minus 1 z to the power 1. So if you basically you are getting what? A minus 1 z to the power n, that is this term. So this term is the repeated term. If you take this common, then first time will get us, if you take this term common, then what will you get? A to the power infinity, sorry, infinity z infinity like this, then a minus 1 z plus 1, and last term will be a z. So this simplifies to 1 by 1 minus a z inverse. In other words, z by z minus a, and the ROC is given by, this is the common term, so a minus 1 z less than 1, so z mod z less than equal to mod a. So this is the ROC. As you can see, in the previous example, z transform was z by z minus a, but in that case mod z was greater than a, but here mod z is less than a. So for left hand sequence as well as right hand sequence, the z transforms are same, but ROC is different. Let us move to the next slide. We had considered left hand sequence, so let us consider the stability and ROC for a left hand sequence. This was the sequence that we have considered. So for a 1.1, you can see the z plane diagram, that ROC is outside the unit circle. That means, in other words, ROC includes the unit circle. So if the ROC includes the unit circle, the signal is stable. But when a is equal to 0.9, ROC is inside the unit circle. So this is the pole and this is the 0. So if the ROC includes does not include the unit circle, then the system will be unstable. Now let us summarize the properties of ROC as we have derived from the left hand and right hand sequence. ROC is a angular ring in the z plane centered above the origin, which is equivalent to a vertical strip in the S plane, as we have derived the Z transform from the Laplace transform. If you recall, the left hand side is represented inside the unit circle. So from that we can say equivalent to vertical strip in the S plane. The ROC is an angular ring in the Z plane centered above the origin. ROC does not contain any poles. This is also similar to the Laplace transform. And if xn is of finite duration, then the ROC is the entire Z plane except possibly z equal to 0 or z equal to infinity. For these two range, ROC doesn't this Z transform doesn't exist. Okay. Now consider that this is the Z transform formula. that is xn given by summation n equal to minus infinity xn z to the power of minus n. For discrete time domain, what we write? In square bracket xn equal to delta n. For delta n, z transform will be 1. For delta n minus 1, it will be z to the power minus 1. For xn to delta n plus 1, it will be xz equal to z. For delta n, ROC is all values of z. For delta n minus 1, ROC all values of z except z equal to not equal to 0. And delta n plus 1, all values of z only except z not equal to infinity. If it is continuous time information, then Laplace transform is given by s is equal to 1. As you can see, z transform and Laplace transform both are same. If time domain delta t minus t, Laplace transform given by e to the power minus st, real value not equal to minus infinity, and e to the power st not equal to infinity. Just a second. Let us see the conclusion. If xn is a right hand sequence and if mod z is equal to r0, that is the radius of the unit circle, this is in the ROC, then all values of z for which mod z greater than r0 are also in the ROC. And if xn equal to left side sequence and if mod z is equal to r0 is in the ROC, then all values of z for which mod z less than r0 is also in the ROC. So as you can see, for right hand sequence mod z greater than r0, for left hand sequence mod z less than r0. Now properties of ROC continued. If xn is two-sided sequence, that is if we add right hand sequence plus left hand sequence, then if mod z is equal to r0 in the ROC, then the ROC consists of a ring of z plane including z equal to r0. That is, we have to march. This is right hand sequence ROC, this is the left hand sequence ROC. If you put this one over here, you will get this one. So you cannot have two ROC at the same time. So if we take this superimposed, that means this only this part is the ROC. That means ROC is a ring. ROC is a ring. For example, xn equal to b mod n. Please note that this is b mod n. So if you take mod n means it can be written as b n un plus b minus n u minus n. So right hand sequence, left hand sequence. This is right, this is left. So if you simplify, you get for the right hand sequence you get 1 by 1 minus b z minus 1, and for left hand sequence you get minus 1 minus b minus 1 z minus 1. So you get the ROC as ring. So mod z greater than 1 by b but less than b. Now properties of z transform. We will discuss the properties of z transform in the next class. Let us get the summary once again. Definition of z transform: x is equal to summation n equal to minus infinity xn z to the power minus n. Then the explanation of ROC, that is region of convergence. Region of convergence, that is ROC. ROC. And its relationship to the existence of DTFT and stability is already shown. And we are talking about DTFT means again we are also talking about actually z transform when r is equal to r e j omega. If we replace r is equal to 1, then becomes z transform. Properties of z transform: linearity property, time shifting property, multiplication by n. These are the most basic properties of z transform. Apart from this z transform, we have other properties which we will discuss in the next class in detail. Thank you for your attention.